So hello everyone. So in the previous sessions we have been discussing about probability and we'll be continuing our discussion on probability. So just a little bit of revision. In the previous session the whole topic was basically on Bayes theorem. So in that the most important concepts that we saw was conditional probability, and then with that we saw multiplication rule or multiplicative rule, and then we saw total probability. This is what we saw, and by using these we sort of went to the Bayes theorem. From that perspective we understood it. So the main thing that I wanted you to remember is, with new evidence you update your belief and do not change it, brother. So on getting some new evidence we don't change our beliefs, but we rather what we do is we just update the belief. So conditional probability was if something happened and then we had some probability of other events. So this was denoted by probability of A given B. That is probability that B has happened. What's the probability that now A will happen? Then multiplicative rule. It was just we got this out of the out of this conditional probability. If we just expand it out, probability of A given B. So we wrote it like this: probability of A intersection B divided by probability of B. So from this we can write that probability of A intersection B is equal probability of A given B. Okay, or this is also equal to probability of B given A. So this should be A given B, this should be B, this should be A, and B given A. Okay, so this is what we wrote, and then we also saw total probability. So in which an event was there which was sort of distributed towards different events, and then we saw how to compute the total probability. In this we saw many concepts. This was sort of a mini revision for the previous lecture that we did. Now we'll do some questions onto it so that I at least have satisfaction that you people know this. So we'll start with the question 1. So have your pen and paper ready. So question 1 goes like this. There is the laboratory. Okay, a blood test is conducted. Okay, it is 95% effective. The test is 95% effective in detecting a certain disease. So if there are disease, it detects with 95% accuracy. So however, the test also yields false positives, which we discussed, like we have been doing this problem. Okay, and also it yields a result for 1%, and false positive rate is 1%. Okay, 95% means that when there is actually the disease, it is effective 95% times, but also there are the false positives which are 1% of the healthy persons. And if 0.5% of the population actually has the disease, so question goes like this: if we have 0.5% of the population which actually has the disease, what's the probability that a person has disease given the test is positive? Okay, this question we have done. I just wanted you to at least form your mental models and do this. Again, I'll repeat the question. The question goes like this: a laboratory blood test is 95% effective in detecting a certain disease when it is in fact, that is, if there is a disease, 95% times that the test detects that disease. However, the test also yields a false positive. So the false positive rate is this much. This is false positive rate. So 1% of the times it yields false positive. And then if 0.5% of the population actually has the disease, so the 0.5% of population is believed to have this disease. 0.5% of the population is believed to have this disease. What is the probability that a person actually has this disease if if given that the test was conducted on him and he came out to be positive? That's the first step. The first step is mathematical modeling. We have discussed this in detail. Why should we mathematically model? Because then we can play with the rules. So let's suppose we'll call event D. D means a person is that, let's suppose we'll call this event D as the person tested has the disease. Okay, this is that event. Then we can also have another event called as E, in which we'll say the test was positive. Okay, this is test was positive. This is person has disease. Okay, now I have mathematically modeled. I have at least brought two variables. I have named now these English statements in a one word thing. Okay, that these things we'll call random variables. When we'll go shift to next topic, we'll call these things as random variables there. Okay, now if I write something like this, probability of D, this means probability that person has the disease. If I write probability of E, this now means the probability the test was positive, something like this. Now, okay, what does the question ask us? The question is asking us, if the person was tested positive, if the person is tested positive, what is the probability that he actually has the disease? So what should I write? If person was tested positive, probability of dash dash
D, D,
D
D slash
D given E, because
E.
D given E. Now we brought this problem into the mathematical modeling. Now you can use the rules. From this you know the rules. So the rules are, you can just expand it by using probability of D intersection E divided by probability of E. Okay, this is equal to, sometimes people also write it probability D comma E, or even they omit the comma. In some books you will see this probability of E. Now we have to compute this. Okay, so how to compute the total probability? Tell me this. Or even you can also make the modeling of this. If you again have to solve this problem, if you don't have that picture in your mind, so you can make it like this. So person has the disease, like here you'll make one branch, person does not have the disease. Then test was conducted, test was positive, test was negative. Okay, again test was positive, test was negative. Can also make this tree diagram, because these are sequential effects. I told you that we can, the many problems in the probability will be sequential. You will have to do one after the other. So first, what is the probability that person will be diseased? So this, let's suppose we'll write it disease and disease complement. Okay, then this will be test and test complement. Test was not positive, so this is test and test complement. Okay, now we assign the probabilities to each of the branches. So okay, what is the probability that person will have the disease? So what percentage of people have the disease? 0.005. So this is 0.005, and then this is 1 minus 0.005, because 0.5% of the population has the disease. Okay, and then what is the possibility that the disease will get detected if it is actually disease? So it is 0.95%, 95%, 0.95%. So here it will be 1 minus 0.9, that will be 0.05%. Again, from this perspective, if it is, this is now false positive. So if you see it from here, so what is the probability that it will be a false positive? So a person did not have the disease, but it still was detected. It is 1%. Okay, so that is 0.01%. And what is this? And it will be 1 minus. So this will be 0.99, I think. Okay. So is it clear now how I made this? Is it clear? This
Yes,
portion
sir.
over here. Now it will be easy to solve the problem. Sorry. So now we'll first find the total probability. Tell me how to compute the total probability. Let's compute probability of E first. So probability of E means test was positive. So where is the test positive? Test is positive over here, and test is positive over here. Okay, if you remember this example. And then I have to compute probability of D intersection E. Can you compute both of these probabilities? Give me the answer for these probabilities. Tell me in the words first. So what will be the probability if you go it over here? So this will be first probability of disease, huh?
जी सर
And then
disease
probability of disease given E happened, is it? Plus
probability of disease
probability of
given
not
partially
disease,
sir
huh?
जी sir
And multiplied by probability of not disease given
given E
this is it happened. So what is the value of this probability of disease?
0.95
0.95. Okay, keep on saying it. 0.95 multiplied by probability of disease given E. So what is the value of this?
0 0.005
0.005. And then plus, what is the probability of D complement? 0.01, I
1
think.
yes sir
Multiplied by, what is the probability of this?
1
0.995. 1 minus that thing, huh?
yes sir
So this is the so this is equal to something. Okay. Then what is the probability of D intersection E? This is probability of D
probability of D into probability of D given E
given E. Huh? That we have already computed this much. This is 0.95 multiplied by 0.005. So this now on dividing, it will be equal to 0.323 on dividing both of these. I hope that this question was clear to you. Okay. Now I'll move on to a simple question that totally you guys will do it. I just again just revise these things. So this is question 2 for your practice. So let's suppose, and this will be a real world example. Let's suppose you are working for a company and that time you have to offer insurance to the people. And if you see online websites, so that you will have to fill in the details and then they will tell you how much premium you should pay for the insurance or something like that. So these insurance companies and other companies who offer some services on based of premium or something, so they evaluate this risk. Okay, that's what they do, and you probably will be doing some real world problem based on this. So what's the question goes like this: an insurance company believes that people can be divided into two classes. So upfront they believe this, that if we have people, so we can sort of divide people into two categories. So one class is that disease prone, so they have high chance of getting disease. So this is disease prone. Okay, and maybe high, we'll say high chance disease and low diseased. So they are categorizing people into two classes: those who are accident prone or disease prone, and those who are not. The company has now statistics, so they have collected a humongous amount of data, because this company might be operating, let's suppose, for a couple of years, maybe at least 50s of years or so something. So they have their own data, and from that data they can conclude something. So what they have concluded is that this accident prone person will have an accident at some time with a fixed 1 year period with probability of 0.4. So the person who has high chance of getting a disease, so within 1 year the probability of having a disease is 0.4. Okay, this is one thing that they have concluded from their statistics. And the second thing is, with for these low disease people, they have said that they'll met an accident or have some disease with the probability of zero point 0.2 within a fixed period of 1 year. Okay, so in general there is an assumption that 30% of the population is accident prone or disease prone. So 30% of the population actually meets an accident per year, or gets diseased per year. Now they will have to offer premium, or maybe they'll have to offer plans based on this. So now what is the probability that the policy holder, whoever the policy gets, so a person will get some policy, so what is the probability that new policy holder will have an accident within 1 year of purchasing the policy? This is the question. So everything is here. So we have been given that what is the chance of a person who is really prone to disease, it is 0.4, and for the low disease people it is 0.2 within a 1 year. And now company also has a prior belief. They believe that 30% of the population actually meets with an accident or has a disease within the fixed 1 year period. So the question now is, if let's suppose person purchased my policy, okay, if person purchased the policy, so what is the probability that the new policy holder will have an accident within 1 year of purchasing the policy? That's the question. Okay, the question is probability of meeting an accident given that he purchased the policy. Now you'll have to tell me the answer of this. Okay, so tell me, Zakir, how do I make this tree diagram?
Sir, we'll first model the problem. Its probability of having high disease is 0.4.
Okay, so first we'll see there is some prior belief. Population has disease or has not. So we'll write disease and not disease, something like this.
Yes, sir.
Okay, and there is some belief for this. So what is the belief? So that is 0.3 population actually meets an accident or has a disease, 0.3, and this is 0.7 then.
Right, sir.
And after that,
high disease, not having high disease.
So there are chances of disease, or there is chance of no disease, something like this, like a chance, high chance and low chance. Okay, after that what should we do?
This will be the first branch will be probability of having high disease is 0.4.
So should I write 0.4 over here?
Yes, sir.
Okay.
This will be 0.6.
This is 0.6. Beautiful. So what is this?
This is 0.2 and 0.8.
0.2 and 0.8. Nice. So if you have done this much, the problem is done, because you understood the problem. The thing was that for these high disease people, so what is the probability that they will actually get a disease within the year? So that was 0.4. So that's what they were given. Okay, this was our prior belief. Within the population, there are 30% of the people who actually meet with an accident or have a disease within a year, within that span of time. So that's what we model. D people means who have disease. D complement means who does not have the disease. And then now we'll see with 0.4 probability, because these people have high chance of getting the disease. So that's 0.4 and 0.6. And now this is 0.2 and 0.8. So what does this leaf represent? Tell me the representation. Now I'll probably move on to Asrar. Asrar, tell me, what does this leaf represent, the first leaf? Probability of what and what?
Probability of having the disease and the other one was meeting an accident.
Probably like this is the belief that they will meet an accident. Okay, this probability means a person was this person is believed to be disease prone. Okay, and this is disease person and this is disease prone and he was disease prone person. Let's also like introduce some other way. Let's call this A even. Let's all suppose this is A. This is be A. This is A complement. This will be A and A complement. So mathematically, even if we are at loss of words, so what we can write, that's the beauty of math. So even if you cannot put it in a language, so you can directly write what is the probability here. So probability will be D intersection A. Okay, and for this the probability will be probability D intersection A complement, and this will be probability of D complement intersection A. This is probability D complement intersection A complement. So first tell me what do I have to compute? The question that I asked was what is the probability of meeting an accident given that the plan was purchased, or meeting an accident or having a disease. So that was the question. So in which two scenarios does the person catch the disease? And there are only two scenarios. In the first scenario here, okay, and I think in this scenario, if you see it, in these two scenarios, the people get the disease after getting registered with the policy. So I have to compute, let's suppose, probability that the person has the person actually got his policy registered, and then I have to see what's the probability of disease. Basically, this is the question of, if you see it, we have now two events, a sort of total probability question. Okay, isn't it? Like, can you see it's a question of total probability? Even you don't have to fully use this. You don't have to fully use the base here. You just have to compute the total probability. Maybe you have to compute the probability of A. That is, person actually got the disease. That's where this A is and A is. How many of you understood this?
Sir.
Okay, now what's the probability? I just add up the probability of these two branches. So 0.3 multiplied by 0.4 plus, I think, 0.7 multiplied by 0.2. That's it. This is the answer. So how many of you understood this now? Okay, so I hope that everybody understood. Now you will have to do this question. Now this is the second part of this question. The second part is, suppose the new policy holder had an accident now. So had an accident or met a disease. Okay, so what is the probability that he or she actually was accident prone or was high diseased? So probability of meeting an accident. So they met an accident. Let's suppose probability of A, because we have denoted that by A. Probability of A, given that given that the policyholder met an accident. So what's the probability he or she was disease prone? This is what you have to compute. So how will you compute this?
Sir, repeat करना question थोड़ा.
The question was, suppose the new policyholder has an accident. So he met an accident. What is the probability that he or she is accident prone? Accident prone means high disease, which we call the high disease, or accident prone, or disease prone. So what is the probability that he belongs into this category? Question is question clear?
Yes, sir.
I even gave you the modeling also. So this is the step that you had to do. So here we said that D is the event, person is disease prone. Okay, and then I said A is that meeting with an accident, meeting with an accident or disease, accident or disease. These are the two things that I decided. A and D, that's what I wrote here. D disease, D complement, not diseased. A means met an accident or has the disease. A complement means the complement of that thing. So here the question was, what is the probability that if a new accident, a policyholder met an accident, what is the probability that he actually was from the disease prone or accident prone portion? So basically you have to tell me the probability, like if he met an accident. So if you see this tree diagram over here. Asrar, so how to compute this?
It will be, sir, probability of D intersection A and divide
Divided
by
by
probability of A.
probability of A. The probability of A we computed, I think. This is the
We
probability of
completed
A.
it.
Now, how to compute this probability of D intersection A? So this is over here, the first
0,
part. 0.3,
0.3 into 0.4
yes, 0.3 multiplied by 0.4 divided by 0.3 multiplied by 0.4 plus
plus
0.7 multiplied by 0.2.
0.2.
This is what. Have you seen even now you don't need to apply your intuition. That's what I was saying. The beauty of maths is initially you first bring the problem into the maths. When you sort of understood the problem and then you try to mathematically model it, once you model the thing, then you know the rules. Then you know the rule of this. This basically is the conditional probability, or I can say this is Bayes' theorem. So once you got that rule, and after that you just use this, and this even you expand it actually. So you did probability of D, or probability of D multiplied by probability of A given D. Okay, divided by probability of A. Then when you expanded this also, so now you know all the rules of this probability, and you easily can come up with the answer. The first important step is how can you mathematically model the problem. That's the most important step. Okay. Now I hope that at least with these couple of problems you got a good grip. So I'll just again tell you the general template. So whenever you have such problems where you feel that some conditioning is happening, so there is some condition is meeting, like some event is happening, then I'm asked to compute the probability of something. So first see if you can construct this tree diagram. Okay, see this. If you can construct this, the problem becomes really easy. Okay, and you also have to give this number, give these letters to these huge English sentences. Okay, and within the next couple of lectures we'll call them random variables or things like that. Okay, but this is the main if I say main crux of the lecture. So given a problem, bring it in the mathematics and then try to construct this tree, assign the probability to different branch, and then play with the rules, whatever rules you have studied so far, then use those rules to compute the probability.